All right, everyone, we're going to go ahead and learn how to graph using a table today. So we're going to graph a function, in this case, y equals 1/2 times x, okay, with a given domain of 0, 2, 4, 6, 8. So yeah, you can look to the bottom of page 5. You're going to see a graph there as well as a little bit of the table. So what we're going to do, we're going to go ahead and plug in these numbers for x. Let's do that. We're going to have 0, 2, 4, 6, and 8. Okay, these are the only x values that we're going to use because it specifically says in the problem that this is the domain. Okay, these are the only x values we care about. So what we're going to do is we're going to plug in these x values and we're going to see what we get for y. All right, so we're going to start by plugging in 0. So y equals 1/2 times 0. So when we do that, y comes out to just equal 0. So we'll put 0. When we do 2, let me go ahead and move this down. When we plug in 2, we're going to go ahead and multiply 1/2 times 2, and that gets us just 1. All right, let's keep it going. When we plug in 4, half of 4 is just 2, half of 6 is 3, and half of 8 is 4. Okay, so we get some ordered pairs out of this, right? This one right here, we have 0, 0. Here we have 2, 1. Here we have 4, 2. Just giving myself some room to write, so I'm writing it diagonally. And 8, 4. Okay, so we're going to go ahead and graph these points. Okay, here we have just quadrant 1. So here's our x-axis and here's our y-axis. So let's go ahead and count. So this is just 0, 0 at first. 2, 1, 2, 3, 4, 2, 6, 3, and 8, 4. Okay, and you'll notice that this is in a straight line. You should notice that whenever we graph functions, okay, linear functions, we're going to get them in a straight line. If you have one that's like off to the side, like right here, you did something wrong and you should recheck that point that, looks a little bit, like it doesn't fit. So the next question is, are we going to connect this with a line of any sort, or are we just going to leave them as points? And what we're going to do is we're going to leave them just as points because the domain was specified as just these ordered pairs. When it's just specific points or numbers for the domain, we're going to get just ordered pairs, and then the matching range would just be this set of numbers right here. Okay, so you'll notice that domain matches the range, or the range matches the domain. All right, so that's it for this problem. That's it, nothing else. All right, let's go ahead and take a look at the top of page 6. On top of page 6, we have another table. And so we're going to graph the function y equals 2x minus 1. You can feel free, with this domain, by the way, 1, 2, 3, 4, 5. So you can feel free to pause the video if you want, just to go ahead and do this problem. I'm going to go ahead and just solve it right here. So when we plug in 1 here, let me go ahead and move this down once again. Our result for y is going to be 2 minus 1, which is 1. When we plug in 2, we're going to get 4 minus 1, which is 3. We can plug in 3 here, and it's going to be 6 minus 1, or 5. When we plug in 4 here, it's going to be 8 minus 1, it's 7, and 5 times 2 is 10 minus 1, which is 9. I'll write it in. So it's 10 minus 1, or 9. All right, so once again, we're going to go ahead and graph this. So on our quadrant 1, we're going to go over 1, up 1, over 2, up 3, over 3, up 5, 4, 7, and 5, 9. Cool. So once again, this is in a straight line. Because the domain was given as 1, 2, 3, 4, 5, we are just going to leave them as points, not connect them. And that's it. Okay, if it asks for range, our range would be 1, 3, 5, 7, 9. Okay, just those ordered pairs. The question I often ask is, hey, could we have plugged in 6 if we wanted to for x? And the answer is no, because this was our specified domain, only those 5 points. All right, let's keep it going. We're going to go ahead and skip this problem for now. We're actually going to come back to it at the very end. So let's go to this one. All right, at the top of page 7, it is asking us to write a rule. So we're going to write an equation, function, for the given graph with these ordered pairs. So my recommendation is go ahead and write out what these ordered pairs are. Okay, we have 1, 2. Make sure you don't switch up the x's and y's. We go, on the x-axis first. So up 1 over, or up, right 1, up 2. We're going to go 2 on the x and 3 up the y. So 2, 3, and we have 3, 4, 5, 6. Is that all of them? Did I miss one? 1, 2, 3, 4, 5. I must have missed one. Yeah, I did. So we have 4, 5, and 5, 6. Oops. Thought that would work. All right, 4, 5, there you go. All right, so we're gonna go ahead and look, just like we did last class, trying to figure out what is happening when we go from x to y, okay? It's always gonna be y equals, our output depends on what we do with our x. So going in this direction, we're always gonna check for addition and subtraction first. +1 would work here. Does that work here? Yes, it does. So +1, that is just our, what we're doing. So we're taking x and we're adding 1 to it. All right, so that's our function. You can check it here. Plug in 5 for x, add 1 to it. We do, in fact, get 6. So this does work. Okay, so here is our rule and our equation. All right, let's check the bottom of page 7. This is where we're going to test use the vertical line test to tell if a given graph is a function. So if you remember last time, we had said that a function was a set of ordered pairs or a relation where the x values do not repeat. Okay, so in this case, 1, 2, 3, 4, 5, this is a function, right? So when looking at a graph, we're going to use the vertical line test essentially to test the same thing. So what that means is we're going to take a vertical line, and this is our red line right here, and we're going to pass it through our entire line. If at any, as long as it goes through and never touches the line twice at one time, then it is good. It passes the vertical line test and it is a function. So in this case, we don't count the arrow right here. That doesn't, count. So at no point does this ever, the vertical line touch the line twice. So this does pass the vertical line test. So yes, this is a function. Let's keep it going through to this one. Okay, this once again never touches twice. Again, we ignore the arrows. So this is a function as well. This one right here, a little more questionable, especially at the beginning and end. Nope, still good. Still good here. So this is still a function as well. Let's go ahead and check down here. All right, here we go. So this, if you notice, has a point here and here at the same time. Okay, it actually happens multiple times in here. And what this is doing, so this does not pass the vertical line test, and therefore it's not a function. And just to bring it back to what we had said about no repeating x values, we'll check this out, right? This right here, if we were just make up an ordered pair for it, 1, 2, maybe 1, 2, 3. This is like 2, 3, and this one right here is like 2, 5. Okay, again, I'm just making up points for it, but the point is to show that, look at this, we have 2 x values that are the same in this function. All right, right here, this one definitely doesn't work. Every single one is on that same x value. This is not a function, and then this one is not a function either. Okay, these ordered pairs fall on the same x value, so this is not a function. Okay, so all the ones on the top they pass the vertical line test. All the ones on the bottom don't pass the vertical line test and therefore are not functions. All right, let's take a look at our last one. This is on page 6, jumping back a little bit on the bottom. So this problem says, the table below shows the average SAT scores from 1997 to 2003 as a function of the time in T years since 1997. In the table, 0 corresponds to the year 1997 and 1 corresponds to the year 1998. Graph this function. All right, so they do something very important here. Actually, before I even get to that, it's the year since 1997. Before I get to that, let's go ahead and look at this phrase they use, as a function of. Here it is, as a function of. Remember we said it's always y as a function of x. Let me write that down. Y as a function, we'll move this in a second, of x. And what that means is everything that was said before the phrase as a function of is your y. So in this case, y, it says average SAT scores from 1997, that's your y, as a function of the time in T years. So that's why this right here is your x and this is your y. Okay, so it's very important. All right, so what we're gonna do is we're gonna go ahead and graph these points. An important thing to note that they had done was they changed the x. Instead of saying years and writing 1997, 1998, 1999, 2000, they changed it to years since whatever the first year was, 1997. So this is something important that we're gonna do if we're ever given a set of data. We're gonna do the same thing. And the idea here is to make it so our x doesn't start at 1997 over here, right? We don't wanna count by 1997, 1998, 1999, because we're essentially jumping from 0 to 1997, okay? So what we do is we change it from years to years since whatever the first year was, okay? So now 1997 is 0 years since 1997. Okay, so this one represents 1997. 1 year from 1997 was 98. 2 years from there was 99, and so on and so forth. Okay, so this is something we're going to have to do in the future. When given a bunch of years, we're going to actually change it to years since 1997. So we'll remember this. So one other thing you'll notice here for the y-axis, we used a break. Okay, the reason here, if you remember what a break does, it jumps from 0 all the way up to 510. Okay, so it skips a bunch of data there. We use this when our data is very confined. In this case, we go from 511 to 519. That's only like a jump of 8, right? But in order to, say we weren't using a break, if we were to fit all of this on our graph, we would have to count by probably like, 50 or 100 here. And then all of our data is going to be in one spot, right? Imagine for a second we have like 100, 200, 300, 400, 500, yeah, maybe 50s would work better here, but still will prove my point. They would all basically be right here in this same exact spot. And we don't really like that, right? We want to spread our data out. So the fact that these are all within just 8 apart, what we're going to do is we're going to break all the way up to 510, and then we're going to count by, in this case, I counted by ones. So we don't want to do that on our horizontal axis, our x-axis ever. We really just stick to doing that on our y-axis. It's very rare that we want to do that on our x. So let's go ahead and finally plot these points. Let's see here. So we have 0, 5, 11, 0, 5, 11 right here, 1, 5, 12, 2, 5, 11, 3, 5, 12, 4, 5, 5, 14, 5, 5, 16 right here, and 6, 5, 19. All right, so there you go. We've plotted our values. We're not going to do anything more with this right now. This is essentially all we're going to leave it. But as you can kind of see, it does appear that as the years go on, the average SAT scores seem to be rising, right? So that's all we're going to really do right here. And that's it for today. Okay, so you have a couple problems to do for homework, but this is the idea of graphing from a table.